Hello, my name is Egor Iuganov. In this presentation I would like to give a brief overview of what I've been working on this year. First, my group and I collected a significant amount of data. We collected it at 3 locations: Mpala Conservancy in Kenya, Wilhelm Zoo in Germany, and the Autobahn National Park in Hungary. The data includes hundreds of hours of drone and ground camera high-resolution video footage, as well as metadata, including camera poses. Much of this footage is multi-view, meaning we observe the same animals with different cameras at the same time. We have developed pipelines to synchronize these videos, as well as to perform semi-automated data annotation and pre-processing. We have also done some high-level manual annotations of these videos. In these pictures you can see examples of the footage we collected. The timeline at the bottom of the slide demonstrates an example of how many animals we observed from different viewpoints at the same time. After the videos are synchronized, we can visualize how our cameras move in space. Here you can see one example. Next, I would like to talk about the pipeline we created for pose estimation. Videos from several cameras are used as an input. After synchronization, semi-automated bounding box annotation is performed. Next, 2D animal features are extracted. Finally, articulated pose estimation is performed. I will now talk about each of these steps individually. We tested the Detector object detector but did not get satisfactory results on our data. Since it was challenging to retrain, we eventually opted for the more lightweight SSD multibox as our detector of choice. We fine-tuned it on our data, which helped us significantly improve its performance. We created a semi-automated annotation pipeline, which uses SSD multibox as well as the RE3 object tracker to quickly create high-quality annotations. To detect 2D features of animals, such as feet, ears, tail, and others, we trained DeepLabCut on our data. We chose ResNet 50 as the underlying architecture. These features are later used to estimate animal pose. We compared several frameworks for animal pose estimation and opted for the fitting-based method called Smaller. However, we transferred the optimization pipeline from ChumpPy to PyTorch in analogy with SmallifyX. This allowed us to take advantage of modern PyTorch-compatible tools and improved optimization performance. In this picture, an example of animal pose estimation is demonstrated. The 3D features of the animal model are projected to the 2D image plane and are optimized in such ways to fit data from the feature detector. The procedure is as following. First, animal position is initialized so as to match the video evidence and to be close to the ground plane. Next, animal position and rotation are optimized to match the 2D key points. Finally, articulated pose is optimized. This is repeated for each frame. Reliable pose estimation is a challenging task, and errors at each stage result in a noisy output. To improve it, we are now refining the stages of our pipeline, as well as introducing additional priors. Thank you for your attention.